the ability to speed up and slow down allows you to evade your opponent. If you're on offense, you can quickly get around the defense. If you're on defense, you can quickly get around the offense. Units for acceleration, meters per second squared in SI units. In US customary units, it's feet per second squared. Let's do a calculation for acceleration. Let's say a car starts with a speed of 10 meters per second. It accelerates to 30 meters per second constantly in 6 seconds. What is the acceleration of the car? Well, 10 to 30, the change in velocity was 20 meters per second. 30 minus 10 is 20. We did that in 6 seconds. That gave us an acceleration of 3.3 meters per second squared. That's quite a high acceleration for a car. Calculating velocity. Let's say here's our acceleration. We want to calculate for our velocity or a change in velocity. A person who starts at rest and accelerates at a rate of 3 meters per second squared for 2 seconds. How fast is he or she running after 2 seconds? Well, if we can solve for v here, v is equal to acceleration times time. The acceleration is 3 meters per second squared. The time is 2 seconds. That means that they change their velocity by 6 meters per second. If they're at rest at first, that change of 6 becomes their actual velocity. Now, when we graph velocity as a function of time, the slope now becomes the acceleration. Do you see this pattern here? Distance is a function of time, the slope or the rate of change is the velocity. But velocity as a function of time, the slope becomes our acceleration. So here we see our change in velocity is 50 meters per second. We do this in 10 seconds. That's our slope. As long as this is a line here, okay, that slope is constant and our acceleration is constant also. Again, here's a graph. This time its velocity is a function of time. So when the slope becomes 0, our acceleration is also 0. Increasing acceleration would be an upward curve like this, where the slope is getting steeper. Decreasing acceleration would mean that the slope is becoming less. Here's a sprinter once again, leaving the start block. He initially started at 0. Pushing off the start block, they can get a very large acceleration. As they accelerate down the track and get closer to the top speed, you notice that the slope becomes less and less. Eventually, the slope becomes 0, at which point they're no longer speeding up, they begin to slow down. Back to our Falcon Heavy. When we graphed distance as a function of time, we got this graph. Smaller slope at the beginning, larger slope at the end. Now we can also graph velocity as a function of time and see what the acceleration is doing. This is interesting. Follow the blue because that's the total acceleration that's going on. Okay? The velocity is becoming greater and greater, but the slope is becoming steeper and steeper. That's because during the flight, the rocket is burning up fuel. It's becoming lighter and lighter until the boosters on the side, the 2 rocket engines on the side, run out of fuel and are completely empty. They cut off and they detach. Notice the graph gets less steep. The slope sort of levels off. Now we just have the central rocket propelling it. Okay? It becomes steeper and steeper as that begins to empty out. And finally, that engine cuts off. It begins to slow down. It becomes level right here, so it's not speeding up or slowing down. And then the second stage engine ignites and begins to accelerate again. Again, rockets are a little bit more difficult to analyze because they're carrying fuel, and as the fuel empties out, they begin to accelerate faster and faster because there's less to push. That'll be very important for when we actually get to our section on Newton's second law and forces. And again, getting earlier on, you can see the larger slopes, higher acceleration, smaller slopes, lower acceleration. Here's acceleration graphed as a function of time. Again, a little more complex. It's harder to see what's going on. But again, you can see the acceleration increases, then the engine turns off. And the acceleration increases, then the engine turns off. And the acceleration increases, again, all while emptying the fuel out. The last thing that we're going to talk about is the acceleration of gravity. This is something that Galileo worked on. Galileo proved that the acceleration of gravity is constant for all objects as long as we can eliminate air resistance. That means that if we graphed velocity as a function of time, we get a nice straight line. It's a myth that Galileo went to the top of the Leaning Tower of Pisa to prove that any object, regardless of its mass, is going to accelerate at a different rate. He actually used inclined planes to do this. Now today we know that things fall at 9.8 meters per second squared, or 32 feet per second squared. Okay? When you're skydiving at first, your acceleration is pretty close to 9.8 because you're in free fall. As you go faster and faster, the upward force of the wind begins to act against the force of gravity. And you actually begin to lose your acceleration. Your acceleration becomes lower, even though you start going faster and faster. Rides like roller coasters and these free fall rides give you the sensation of falling, those butterfly in your stomach sensation, because when you're in free fall, you are accelerating at the same rate of gravity. You no longer feel the force of gravity as you move with it. Here's the speed of fall, roughly if we approximate the acceleration of gravity to be 10 meters per second, but here's the speed of fall as a function of time. Roughly every second that goes by has you falling at nearly 10 meters per second faster, or about 22 miles per hour faster. Okay? It doesn't take very long for you to get going to a very high speed. If you're falling for just 5 seconds, you would have reached 100 miles per hour. Okay? Even a fall of 2 seconds in free fall gets you up around 45 miles per hour, which is usually not survivable if you're hitting a hard surface. What about distance of fall? Well, there is an equation for distance of fall as a function of gravity and time. The distance that you travel is equal to 1/2 g, 9.8 meters per second squared, times time squared. So again, you fall pretty quickly in a short amount of time. You also travel quite a distance in a short amount of time. Okay? It takes you only 2 seconds to fall 20 meters. It takes you, well, let's say about 250 feet. Only 4 seconds to fall 250 feet. Okay? 1,000 feet roughly would take you about 8 seconds to fall. Okay? That's why when people skydive, they're usually skydiving from a fairly high altitude. They want enough time to experience free fall, but not such a short amount of time that they don't have time for their parachute to deploy. If you ever study to be an astronaut, the one thing that you'll have to do is train for 0 Gs. People react to 0 Gs in different ways. Some people get a thrill out of it. Some people become disoriented and nauseous. Before an astronaut can go into space, they train on this KC-135. It's an old Boeing 707 that's been converted, and its nickname is the Vomit Comet. What it does is it goes into these steep curves where at the top of the curve it's technically in free fall. It's actually falling downward, or the pilot is steering it very precisely, so it's accelerating downward at 9.8 meters per second squared. Of course, you've got to pay for that at the end, where at the end you actually experience nearly twice the acceleration of gravity. But this helps astronauts get a feel for what zero gravity is like, so when they actually experience it, they're used to it. Here's a little trick that you can do. You can measure your reaction time. Have a friend hold a ruler, okay? Ask them to drop it at some random time and that you don't know of. They're not going to count. They're just going to randomly just drop it. And you have to grab it. The distance that it moves before you can grab it is related to your reaction time, but not linearly. The distance that it falls is 1/2 gt squared. So if you want to find your reaction time, it's equal to the square root of twice the distance that it falls divided by 9.8. Let's say you let it fall 10 centimeters. That's not a great reaction time. If I put 10 centimeters in here, multiply that by 2, I get 0.2. Divide 0.2 by 10, that gives me 0.02. The square root of 0.02 is equal to 0.14. That's a reaction time of 14 hundredths or 0.14 seconds. Okay? Most people have a reaction time of about 1/10 of a second. So again, want to test your reaction time? Be honest about this. This is an easy way to do that.